let's look at the real behavior. For the real behavior, we'll use the van der Waals expression with a correction to the pressure and volume terms. Now, I'll just do this for carbon dioxide, and you can repeat the calculation for helium, but I can solve for pressure, nRT over the volume term minus the A n squared over V squared term. I can plug in those values, a mole of gas, the ideal gas constant, and the temperature over V minus NB. N is the number of moles, that's 1. So it's the volume minus the parameter B. The whole quantity minus the A parameter, N squared over V squared. N is 1 mole, V is 15 liters. So if I go through and do this calculation, I get a pressure of 1.61 atmospheres at 15 liters for carbon dioxide. Now, if I change to 0.15 liters, 150 milliliters, in both this expression and this expression, and recalculate, I come up with a pressure of 67 atmospheres at 150 milliliters. So let's compare the real and the ideal results. The real behavior at low pressure, that is the big volume, 15 liters, the ideal case, they're the same. Ideal gas, it doesn't matter the identity of the gas. We would predict the same pressure. The real case, when I did it for helium, I came up with nearly the exact same answer to this number of significant figures. So it looks like at this low pressure, helium is behaving ideally in both cases. For carbon dioxide, a small deviation from ideality at this low pressure. What about the high pressure, that small volume, 150 milliliters? We have the ideal case, again, the same for both gases. And for the real case, we have a small deviation, a few tens of percent for helium, but the deviation for carbon dioxide was quite large. So as you go to higher pressure or more extreme conditions, higher pressure, lower volume, where the gas particles are closer together, the real part of the gas, the interactions become more important. So high pressures, low volumes, you expect greater deviations from ideality. And that's what we see here, a pressure of 67 versus 163 atmospheres for the carbon dioxide case. So you can see real versus ideal behavior and apply both the ideal gas expression and the van der Waals real gas expression to calculate pressures for gases.